Okay, the first thing I want to do is explain why my K&J Magnetics Hall sensor here, which is, it's just an old, phone type thing. It had a wireless phone, the old style. It's not cellular, it's just a wireless phone. Gutted it out, put all my parts in there so I could, use it without the board being open to shorting out and such. So that's all comprised inside the phone itself. I had a wire sticking out, 3 wires coming out, and the little Hall sensor is on the tip here. And it's one of these. If you can see it, it's a little Hall sensor with 3 wires. You can see them. You get current goes in the middle wire, and the outside two, or where your current goes either positive or negative, depending on how it's wired through this. And I'm not even sure exactly how this comes out wired as far as the red and black being positive or negative. It depends on how you wire it going in. I think I did it right, according to K&J Magnetics. But these, I bought these 6 of them in a lot of these little Hall sensors. I forget their numbers. They're the P-type style. They're bipolar, which means the north and the south will cause the current to go one way or the other through those little wires on the outside. The north will make it go one way, the south makes it go the other way, depending on which side of the sensor you put which pole on. So what I'm trying to do with this is dispel that my sensor is not off. The reason I get 2 different numbers, one side or the other, depending on which way I turn the pole of the magnet. The problem is these things are made so on mass production that it's not centered. These things are not perfectly centered. They're just there to pick up the signal one way or the other and send it to the right wire, which it does perfectly. It's just not perfectly centered like a high dollar Gauss meter would be. So I'm trying to dispel and explain why my Gauss meter here gives 2 different readings, but I'm going to show you why they're the same, even though there's 2 different ones, okay? So that's the point of part of this, is to show how these little Hall sensors work and why I'm getting the readings I do. I can't find more expensive sensors like this that seem to work with this particular board that K&J set up for this particular size of Hall sensor. So I'm trying to make you understand why I'm getting the different readings I am through the Hall sensor I'm using. It's not the board I've soldered. It's not the voltmeter. It's just these things are mass produced and they're not perfect, okay? So I'm going to move on and show you why it does what it does, and then we'll move on to showing you some of the experiment, and we'll do that. Okay, here's a blown up picture of the Hall sensor, A1302, that goes with these Gauss meters from K&J Magnetics. The reason that I get 2 different numbers is not because the magnets. These are just little semiconductor chips in there. And when the south is on one side, it pulls it one way. It pulls it with the south. And when the north is on it, it pushes it the other way. But if you orient them on, each side, like I'll show, they push the same direction if the magnet's in the same orientation. So here's like a perfect setup of that. When the conductor is pulled, or they call it the electrons, are pulled towards one side or the other, you'll get a positive reading like this. And then take the magnet away, it goes back to center, and these are centered. These are high dollar Hall sensors that are made perfectly. On these mass produced ones, the quality control isn't that good. So here it is the other way, and you notice it leans the same distance towards that. So it's pulling the electrons equally. Well, here's like my sensors, it's mass produced. That's a little off in the center. It's not perfectly centered. I've tried to find other sensors that will work with this board, and they all seem to have a little bit off numbers. And see how it's real close to the red there, and back center, you can still see it's off. And then when it leans to the black here, you're going to see there's a gap. It's going to be like a volume knob. It's not quite turned up as much. That's the difference. That's the only difference. But since the magnets do the same, when you point them orient to north and south in the same direction on either side, it's working. So that's the only problem with these Hall sensors I'm using, is mass production, bad quality control, and they just aren't centered. And we'll move on. Okay, I'm going to run through this again. I'm going to do it a little more explanatory, if you will. And what I've got is a 1-inch neo sphere, a 3/4 neo sphere, a 1/2-inch neo sphere, and a 1/4 inch. And they're all, the blue side is south. If you can see the light coming on. Blues are south. The reds are north. You'll see that they're all going to be the same here. What I want to prove with this particular setup is a couple of things. First of all, the Hall sensor is perfectly good at reading these magnets as they are for whatever readings it gives out. Because if I put the north of the 1-inch up against this side, I get a 2.09, 210, 29, 210. Negative. And if I take the 3/4, 210, 209, 210 negative, the 1/2-inch, this is the north side, 209, 210, north side on the right side of the sensor, okay? I'm going to do them all. I want to show you that's very accurate. The little 1/4 inch, 209, let me get it just right. This one's hard to work with. 209, 210, right there. Now, if I put the south on the other side, the 1/4 inch, I still get a 209, 210. That's the opposite side, right, with the south, okay? And the 1/2-inch, going to do the same thing, 209, 210. The 3/4 on the other side with south now is 209, 210. And the 1-inch on the other side will be 209, 210. It bounces a little bit. So what I'm trying to explain here is they all show the same when the magnet's forcing the charge through it one direction. The north is pushing it that way, so it's a negative, and it's a 209. The south is pulling it that way, and it's still a negative, and it's still a 209. Now, what I'm going to show you that's why this is working fine is because if I spin the magnets and put the south on this side, I'm going to get a 202 or 203 positive. But if I put the north on that side, I still get a 202, 203 positive. I've reversed the direction of the magnets moving the current, the magnetic field, through the Hall sensor to make it work like I showed you. See, it's opposite. The north on this side is going to show a negative 209. The north on that side is going to show a positive 202. And the south does the same thing. On this side, it's a positive 202, and on this side, it's a negative 209. It just depends, and this will do the same thing. North on this side is a negative 209. South on this side is a positive 202. North on that side is a positive 202, and south on that side is going to be a negative 209. They all do it. I'll even go to this one, the little 1/2-inch. North on this side, negative 209. South on that side, negative 209. Reverse that. South on this side, positive 202. North on that side, positive 202. So what I'm trying to say is these sensors are a little off center. When it goes one way through it in a particular direction, you get a little higher reading than you do when it goes through the other way. That's the only difference. These are mass produced, so they're not perfectly centered on when it swings. It's like a two-way switch, like I showed you. It either swings one way or the other. Right now, it's swinging that way because it's pushing. And when I put it this way, it's still swinging that way. But I get the same reading, negative, and the same number. Okay? Now, if I flip the magnet, it's swinging towards me. But it's a lower reading, and it's positive. And the same thing here. It's pushing it towards me, lower reading, positive. So, in other words, this works perfectly. It's just that it's mass-produced, and it's not perfectly centered so that each side will show the same. So, in other words, it should be, to split the difference, 2.09, 2.0, or wait a minute, 2.09 this way, or 2.02 that way, 2.03. So you got like 6 numbers different. So it should be like 205, 206. It should be on both sides to be equal. So the magnet's putting out equal pull and push on each side. It's just this Hall sensor is not, perfectly made to discern that. All it wants to discern is which way it's going, and it does that perfect, positive or negative. So I'm just trying to show that. I hope you catch what I'm doing here. The Hall sensors and the board and the meter are working perfectly. It's just the Hall sensor is not really precision made. It's mass produced, but it's very close if you notice. 2.09, maybe 210. On the other side is 2.02, maybe 2.03. So you're talking 5 or 6 digits different. And according to K&J, it's hundreds, thousands, and tens. So you're talking 10 numbers difference, and you split the difference on those 10, and it'd be 5, 5. 2.03 and 2.09, you're talking 6 numbers. Half of that's 3, so like 206 it should be on each side. 205, 206 on each side. Would be perfectly split, perfectly balanced, perfectly equal. But what I'm trying to show you is, even though the north on this side is 209 negative, the south on that side is 209 negative. So they are equal because they're both moving it in the same direction. And if I reverse it, 202, 203 positive, 202, 203 positive. And the numbers are different because of the split, but the positive and negative are which way it's going through, so that those 3 wires, it's either clicking one way or clicking the other way. I hope you get that. It's either pushing it through one way, 209, or pulling it through the same way, 209, or it's pulling it through the other way, 202, 203, and it's pushing it through the other way, 202, 203. So I'm trying to show that this works perfectly. It's just these little Hall sensors are mass produced, and they're not perfectly exact centered for which way that little, it's almost like a switch in there, positive or negative, which wire it sends, which way it leaned to make it either loop negative to positive or positive to negative. So I wanted to get that out of the way before we move on to the next part, and we'll do that. Okay, this is just a quick version of this. This is not the one I'm going to publish. The jig I made is a double bearing situation. It's mounted solid in this bottom 2x4, but there's a bearing here, but it's offset 1 inch. And then there's another bearing up here, which can spin centered on the 1 inch offset. So if you look, it can go around that way, but this top one can also rotate centered in any place that the bottom one is doing the 1 inch, swivel around, if you notice that. So that's the jig I've been working on. I finally got it where I want it. So now I'll show you what I'm doing with the jig, and it's a different angle of view of what's going on here, and we'll move on. Well, before I do that, I've got the Hall sensor back here set right behind on the back side of this jig, and I'll have my voltmeter close, and you'll see everything. And I'm going to get more of a view from straight down so you can see what's going on, and we'll move on and do that. Okay, got the Gauss meter sticking out with my Hall sensor. Here's my device here. Let me move this over just a little so you can still see the numbers, yet I can move around. What I'm going to do is put the 1 inch in here like this. My lines are pretty close on the equatorial plane between south and north, blue south, red's north, of course. But watch the numbers. Over there, we're at negative 209, right? Swinging around. Over here, we're negative 209. Now I can spin this. And on this side, we're positive 202, 203. And on this side, we're going to be positive 202, 203. And that makes perfect sense. But watch. If I get over here, and let me change hands. If I get over here, negative 210 and positive 202. But as I turn towards the equatorial plane, it'll start dropping, 202, 203. There it goes, it's dropping, 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 dropping. And right when I get to the equatorial plane, it's going to go to 0. See how close it's getting? 7, 6, 5, and it went positive. Now there it goes. Right there, 0, if you saw that. It don't stay there. It's hard to hold it there. It just keeps wanting to jump on its own. If you see that, I'm right at 0. If I turn it just right, you don't want to stay on 0. That's at the equatorial plane this way. You see what I'm saying? And it does the same thing on this side, you know, naturally. 202 positive with the south over there, and 209 negative with the north over there. And as I turn towards the equatorial plane, it's going to drop down to 0. My line's a little off. 29, 7, there it goes. 7, 11, 4, 5, 4, 3. See, it's hard, it jumps. But, you know, Ken says it's going to centripetal nothing, and it's not. They're canceling each other out. The pull and push of each side has canceled each other out at the exact split of the equatorial plane on this side view towards the Gauss meter sensor, the Hall sensor, at the position it is. And I think it's not going centripetal to 0. It's just they cancel each other out. Because I can do it on either side, and I'll get down to 0. My point is, watch this now. Out here, it'll go to 0 at the pole. And it'll do it with the other pole. Basically goes to 0. See there, if you're watching. Or I can get it, it won't stay, it jumps. Because I don't have this on a real fine-tuned mechanical situation. But what's odd, watch now, if I'm negative, now watch this, if I'm negative with the south or north to the right, which gives me negative south to the left, okay? If I pull the equatorial plane up there, I will get, let me get my meter set right. I get 100% reverse positive. Look at that, 2.02 positive. You see that? Equatorial plane this way, but with the magnet oriented this way, watch what happens. Over here, I'm 210 negative. Over here, I'm 210 negative. Let me get it centered a little better. 29, 210 negative. 209, 210 negative, but when I get right to the equatorial plane, 100% reversal, 202 positive, as if I've turned the magnet like that. 202, 203 positive, 202, 203 positive. When I get to the equatorial plane this way, it's going to go 209 negative. Do you see that? Right between them, reading with the Hall sensor reading it this way, you see that? It reverses the polarity that it should be when it's this way. 202 positive, 202 positive, 209 negative. It's like I spun the magnet out here. 209 negative. 209, no. I moved it accidentally. 209, 210 negative. 209, 210 negative. When I get right to the equatorial plane, it's going to go 202 positive. Reverse, absolute reverse. Now, if I sneak in, it's going to go negative to the 209, and this way it'll go negative to the 209. But in between, it jumps to positive. You see that? 202, full power, and then it jumps to negative right there. Now, on the sphere, that's what it does. I think right in the middle is showing the back shot of the north being bent back around. Right here is the only place that shows it. You see what I'm saying? It's negative there, it's negative there, it's reversed there. And if I spin it, it's positive there, it's positive there, but it's negative there, and full power. Full power of what these are, but reversed. Do you understand? Do you understand that? It's complete reverse with complete full power at the equatorial plane. That's what's got me boggled on this. Now, that's what the sphere, that's what a sphere does, okay? That's pretty mind-boggling within itself. Now, I have a cylindrical magnet. It's 1 inch by 1 inch, basically the same thing. And if I put it here, look at this. It will do the same exact thing. 210 negative, but over here it's 202 positive, 203, and over here 202 positive. But when I get the equatorial plane, 209 negative. Now if I spin that, I'm going to get 202 positive in the equatorial plane, and I'm going to get 209 negative and 209 negative, 210. Same thing the sphere did because we're curved, okay? But the only place that's actually showing the reversal is right at the equatorial plane between the two. If I move a little bit, it jumps negative. Go back to the middle, positive. If I move a little bit this way, it jumps negative and goes to the full power this way. But right there is full power as if I had turned it. I hope you see that. This does the same thing a sphere does in that orientation. This way, it's basically the same thing, but it reads different. It doesn't read the full power until you get to the side of it. And this one's harder to do. I don't have a jig. I've been working on a jig for this one and working on a jig for the next one I'm going to show you. But this one does tend to not show the same readings that the sphere does. So I'll get a 202 positive, a 202 positive, and in the middle, it jumps around, but this has a hole in it too. So this one, but this way it shows the same thing the sphere does because it is spherical. I understand that. Now here's the weird part. If I take a longer cylindrical magnet, okay, these are all N42s. If I put it here, 209, 210, 209, 210 negative. If I flip it, 202 positive, 203, 202 positive, 203. Now watch this though. When I take this to the side, 203 positive jumps negative all the way along it. All the way along it till you get to the end. Then it will jump positive again. Back up to 203. You see that? It's going to be negative all along there. The whole side is negative till I get to the end, then it turns positive. Back to full power. This one does not show full power at the equatorial plane. Very little, but it's all negative, and it's real close. It gets more powerful down here than it is at the equatorial plane, but it's still negative, if you notice. Let me hold this still. In the middle is the lowest numbers, 24, negative 24, 25. So I move along, the negatives get higher, higher, higher. See that negative higher, higher, until I get to the end, and it jumps positive, right to full power. And it'll do the same the other way, which you can't see if my hand's in the way. I don't know how to do it. Anyway, it's going to do the same thing here till I get to the end, negative and then positive. And if I flip the magnet, where this is negative, you can see it, this will also be negative. But when I get in front, in front of it, it's positive. And the weakest point is at the equatorial plane, 25 again, and it gets stronger as you go, and back, weaker, and stronger as you go, but it's the reverse field of what this shows on the end. Negative, positive, negative, positive. So that's what's got me kind of befuddled, is all along this, on the end of the Hall sensor, it shows negative. I thought it was the rotation. But if the rotation was true, watch this. It does the same thing a sphere does. If I get over here in the center, it goes to 0. You see that? If I go up, I get to my higher point, 1.202, 203, positive. Bring it down, it goes to 0, and then, you know, if I put the south there, it'd be 2010 negative. You know, this and this are the same on this magnet. Side to end. Let me do it over here so you can see. My hand keeps getting in the way. This, 210 negative. And the side, basically 210 negative, if I get it right. But if I get down to the middle, it goes to 0, just like the sphere did on the side in between the things. But up here, this way it does different. So I'm wondering if the rotation has something to do with that. So let me know your thoughts. If I need to redo this somehow, just let me know. All right?